Okay, good morning everyone. Okay, good morning everyone. Before we begin, I would like to ask you a quick question. When you look at the skyline of a modern city, do you see a solution to climate change or do you see the primary cause? Most people are surprised to learn that the very buildings we work in are responsible for nearly 37% of global energy related CO2 emissions. My name is Nur Azira binti Badruddin, and today, alongside my supervisor, Associate Professor Dr. Nurhanim binti Zakaria from the Faculty of Built Environment, University Malaya, I would like to share how we can change that narrative through our research, adapting life cycle costing for energy cost optimization in existing green office buildings, a structural equation modeling approach. Okay, this is my presentation outline. Okay, to set the context, let's look at the current landscape of green excellence in Malaysia. We are seeing iconic structures like Menara MBJB, Diamond Building, Menara Kerjaraya. These buildings represent the pinnacle of sustainable design, yet they also present complex operational challenges that require sophisticated cost management tools. A prime example of this complexity is Menara Sarawak Energy in Kuching. It holds a silver GBI rating for non-residential new construction. Note its unique atrium daylighting system. While this feature significantly reduces the demand for artificial lighting, lowering operational costs, and it requires a specific maintenance approach to remain efficient over time. Okay, the urgency of this study cannot be overstated. Office buildings are among the most energy intensive typologies, yet many fail to achieve their predicted energy savings once they are occupied. According to the IEA, the constructions and building sectors alone accounted for 39% of energy and process related emissions in recent years. We are finding that green by design does not always mean a green in operation. So, this failure contributes directly to the greenhouse effects where trapped gases like CO2 warm our atmosphere. This study matters because, as noted by researchers like Go et al. 2026 and IEA 2025, we must move toward rigorous operational carbon emission assessments and energy audits if we are to meet our sustainable development. Okay. In Malaysia, our framework has evolved significantly since the introduction of the Green Building Index in 2009, followed by the MyCREST and other assessment tools. However, there remains a significant gap in how we calculate the long-term economic value of energy saving features versus their actual operational costs. Okay, the GBI was established by the Malaysian Institute of Architects and the Association of Consulting Engineers to drive sustainability. In their assessment criteria, energy efficiency EE is the most critical pillar, carrying a massive 39% weight of the total score. So this confirms that energy performance is the single most important factor in a building's green rating. So, however, a certificate is only a snapshot in time. The real challenge is managing the critical life cycle cost components that determine whether that building remains cost effective throughout its entire life cycle. Okay, these are the critical life cycle cost components for green office buildings. Where in this study, the selected LCC components were finalized through a systematic literature review and subsequently validated by industry experts to ensure their relevance within the context of green office buildings. Okay, this is the summarize of the research gap. The existing LCC applications are static and financially oriented. Limited integration between EE and lifecycle economics. The green assessment tools provide certification but not the dynamic support decision tool. Few studies empirically validate relationship using SEM. Okay, the aim of the study is to develop an operationally oriented LCC approach for existing green office buildings. Besides that, to integrate LCC components and to support stakeholders in long-term retrofit and operational decisions. Okay. Our methodology involved four stages from the literature review to survey distribution, where we use a quantitative research design targeting a green building experts with a minimum of 5 years of experience. We retain 197 valid responses from professional respondents, including engineers, architects, QS, facility manager, and green building experts. Okay. Okay. The analysis was twofold. The first stage is used to use the relative importance index RII to rank components, and stage 2 utilize Smart PLS 4.0 for PLS SEM analysis. This allows us not only see what experts think it is important, but to see what actually drives the cost model. Okay, these are the demographic profile of respondents, where our respondents were highly qualified with 43.7% having more than 15 years of experience. And we can see here that the most respondents are from our civil engineer with 20.8%. Okay, for the RII value, the construction and installation costs in the context of retrofitting context emerge as the most critical component with the highest RII of 0.762, followed by maintenance and replacement costs. So amongst construction and installation costs related, the most significant criteria identified with high level importance were minimum EE performance, renewable energy, and lighting zoning. Okay, these are the structural model where the PLS-SEM analysis, which include both measurement and structural model evaluation, essentially for hypothesis testing and to ensure the validity and reliability of the construct measured. So all exogenous and endogenous constructs demonstrated strong correlations within their respective measurement models, where in total there were 7 relationship to be assessed, and this table 5 summarizes the findings of the structural model analysis accordingly, where we can see that the variance inflation factor VIF values obtained for all predicted constructs range from 1.854 to 2.661, as shown in this table, which remain below the recommended threshold value of 3. So these results indicate that no significant collinearity issues were present within the structural model. Meanwhile, the relationship between maintenance costs and LCC recorded a strong effect size with a with a F2 value, F square value exceeding 0.35. Okay, for research contribution, this research contributes by transforming LCC from a static cost analysis into a dynamic decision support framework, where it bridged the gap between energy efficiency and life cycle economics, providing a unified model for strategic guidance. Okay, to conclude, energy optimization is driven more by operations and maintenance than by initial capital investments. So our integrated LCC SEM approach provides the evidence needed for sustainable retrofit strategies. For future research, we recommend integrating real-time operation energy data to further refine this decision-making tool. I think that's all for now. Thank you.